下没有这边，等一下有人帮我打中。
我听管。
要有人打，话语的话，不要有人。看哪里，然后再一次。反正
他来抽一张
啊。他是找黑卡。
Okay, good morning. Let's begin this fight. Professor Yu Qingzhong will come here a few minutes later, so let me introduce ourselves first. I'm Zhen Xiande, coming from Donghua University.
I'm James Chen from Taiwan Ocean University.
John Hong from National Taiwan University.
Okay, please everyone introduce yourself. Reporter.
Okay, so dear jurors and debaters, thank you for coming. And my name is Andrew Lee, the captain of the Dock Rangers team. And this is James, this is Jeremy, this is Tony, and this is Blake. Thank you.
The opponent.
Team La Placid, and my name is Li Ting, I'm the captain. He is Wang Guan, and this is Huang Yan, this is Lin Xuanming, and as we have Zheng Lihao. Thank you.
Reviewer. Okay, welcome to this fight. So first, let's begin this fight. Opponent, please challenge the problem to the reporter.
Challenge air muscle number 2.
Number 2.
We accept.
Okay, accept. Please each team write the competitor's name on the blackboard.
好，直接说起来。直接说起来。
完起来。
这个真打好，真打坏。
没关系，
他来骑，他来骑。
你们不说玩开始吗？你们是说会就是开始吗？
一个去玩去。
是502吗？
有去。
我们要记什么？他记。他们那什么 T 那个太细了。
Now the reporter take the stage.
Okay, so greetings. Today I'm gonna report on problem number 2, air muscle. So this is our brief outline. So now let's start with an introduction. Problem statement. Place a balloon inside a cylindrical net, as is sometimes used to wrap garlic, and inflate it. The net will expand and shorten. Investigate the properties of such a muscle. The key questions are, first of all, the muscle properties, which includes both the net and the balloon. And secondly, the function of muscle under stress. Okay, now for intuitive explanations. So this is our original net, and with a balloon inside, and when applied with a force outwards, it will expand in its width. And now for the quantification. So first of all, we'll talk about the net, which includes the length of the net and elasticity. And also we'll talk about the deformation, which includes the opening angle and contract distance. And also we'll talk about the balloon, which is the main source of the pushing force. And now for the quantification of the balloon, we will talk about initial radius, the radius after expansion, the inside pressure, environmental pressure, and the fatigue of the balloon. And for the elasticity of the net, after multiple trials under weight, we can gain that the stretch are small enough to neglect. And now for the balloon's properties. So we use a BMP 280 to measure the pressure inside, and we also use OpenCV to capture the outer frame. And we consider the balloon as an ellipsoid and define the equivalent radius as shown. And for the modeling of tension, we use this equation. Thus, we can gain the differentiation in pressure. And for the modeling part, so first of all, the balloon's volume will always stays constant. And as you can see over here, we define lambda 1, lambda 2, and lambda 3. And we will use the symbol lambda afterwards. And we assume it is quasi-static as the balloon expands slowly during experiment. So we apply Moody-Rivlin model and Laplace law. And when lambda is near 1, we can rewrite lambda as lambda equals 1 plus epsilon, where epsilon is infinitesimal. And as you can see over here, this is the differentiation in pressure. And it is near linear over here, as you can see. And when lambda is greater than 2, as you can see over here, we can use another sort of approximation. And now let's talk a little bit more on the C1 and C2 included in the formerly mentioned formulas. And this is C1. As you can see over here, the balloon is stiff before first expansion. And after the first expansion, you can see that it remains relatively constant. And this is C2. As you can see over here, the gap between 1 and 2, which is the first trial, the second trial, will be rather significant. And this is why the balloon is tight when first expand, and it will eventually decay due to fatigue. So that is why we will have to stretch the balloon before the first application in order to make it practical for usage and predictions. And this is the fitting model. As you can see over here, the first expansion deviates the most, and the pressure stabilizes due to fatigue. And this is the balloon radius. As you can see over here, as time has passed, as we have gained more and more trials, the initial volume increases, which indicates that the balloon gets thinner. And so we previously talked about fatigue, but the quantification of such is pretty essential towards this. So we did an experiment with the same balloon multiple times. And as you can see over here, the initial radius will grow. And so for this experiment, the manipulated variable will include the number of experiments, while the control variable will be the relation of pressure and expansion rate. And as you can see over here, these are not well aligned. Just as we mentioned earlier, as time has passed, due to fatigue, the balloon's initial volume will increase, which indicates their initial radius will not be the same. Hence, we use another sort of calibration, which we use lambda, which is the radius divided by the initial radius as the x-axis. And as you can see over here, the first expansion is relatively weird, which we have mentioned earlier. That is because the balloon is relatively stiff. And as you can see over here, this will get lower and lower due to fatigue. Okay, for our nodule, as you can see over here, the relative error will decay, and that after the first 1 or 2 seconds, you can see that it falls below 5%. And for the radius part, as you can see, they are all within the range of 5%. And they are all within this range, indicating that a radius can be applied with what we say multiple times within the same assumptions after multiple trials. And for this one, I would like to talk a little bit more on the error rates, which you can see over here. We use the 8th, 9th, and 10th experiments for this one, what we say the least 3 data, which actually is the last 3 data. And so after multiple trials, you can see the error rate is falling, indicating that the overall system has been stabilized, and the influences of fatigue is relatively small. And now for the conclusion. After first expansion, the fatigue mostly influences low stress ratio, which is of C2 rather than C1, and we can see that the effect of this fatigue is decaying throughout time. After the 10th experiment, the effect of the fatigue can be neglected, which is what we say lower than 5%. And we will use the same balloon in the following experiments. The model is more effective at high fatigue and long time scales suitable for muscle implementation, which, as you can see earlier, that it tends to stabilize after multiple trials. And now, let's talk about the stress. So this is our experimental setup where we use 1 to 3 springs underneath and an air pump pumping air into the chamber. And we pump the air at such a slow speed that it tends to be sort of quasi-static system. And we use the BMP 280 to measure the pressure. And these are the bricks which is used for stabilizing. And we use the bricks because the fact that the pulling force is so significant that when we use other sorts of stabilizing, the system will directly flip over. And this is the modeling part, where we use Longy theorem to gain the force equations. And as you can see over here, this is a part of the balloon. And we combine this with the previous formulas that we mentioned in order to gain the force equations. And so this is the K-force measurement, where we measure the formation using tracker. And so we track the points and we gain this chart where the spring number 60, number 61, and spring number 62 have the K's shown. And for the experimental video, so as you can see over here, this is the frame using OpenCV. And these are the 3 springs with number 60, number 61, and number 62 respectively. And so these are the results. As you can see over here, we track the dots and mark them as x1, y1, and x2, y2, x3, y3 respectively. And as you can see over here, when we use this, what's that called? Never mind. When we use this equation, you can see that the differentiation in x is relatively small when compared to the differentiation in the y displacement. And this is the YT graph of the one-spring version. And as you can see over here, it is growing throughout time. And as you can see over here, what I mentioned earlier, the time scale. We measured for 30 seconds, so we can assume that it's a quasi-static system. And as you can see over here, when we magnify a small part of the overall, it shows a slow staircase-like climbing, indicating it's close to quasi-static model, which is another proof. And this is the stress observation. As you can see over here, the rate of increasing muscle-generated force decreases over time. And this is resulted from what we mentioned earlier, the fatigue. And the muscle can produce more reaction force when applied a larger external force. And this is the pressure stress graph. As you can see over here, the pressure and force is near linear after after some time. And now for the conclusion. So we explained why the muscle will contract by modeling it in a necklace, which is the frame, as you can see over here. And we talked about the elasticity of the net and the fatigue of the balloon are considered. And as you can see over here, this is the necklace that I mentioned earlier. And we also talked about fatigue and of the balloon and quantified it. And we tended to make sure that the balloon's fatigue is negligible after the 10th experiment. and we explain why the initial radius increase and the wall get thinner. And also, we model expansion and experimentally prove a stop and go movement, which is the graph that I showed earlier, the magnified part, which indicates a slow staircase like climbing. And that's my report. Thank you.
Okay. Your opponent can
Okay,
take
so
turn.
first thing I want to ask is number six. Okay, page six. So you mentioned two F push in the center, and I want to ask why there are two six.
Wait a second.
Okay, so you mentioned two F push in the center. I want to ask why do you have two F push? Right?
Oh, this one and this one?
Yeah.
Oh, this one is F pull, pulling upwards.
Okay.
And this one is
Okay,
F push.
number page eight. So. Okay, so if you plot the graph, but I didn't know why you choose to add leg. If you didn't explain.
Oh, because as you can see over here, as our weight increases, those are staying within this range, which indicates they're pretty small.
Okay, turn to page 20. So you use linear to build this diagram?
No. This arrow is only to show you the trend that the initial volume increases.
Okay, turn to page 25. What does the y-axis mean?
Y-axis?
Yeah.
This is a relative error, which is defined over here.
So this is a pressure relative error.
Yes.
Yeah, okay. You said, do you quantify the input speed to prove your quasi-static input speed?
Input?
Input speed. No, I mean every time your pressure versus the time. Okay.
Pressure versus time domain. Please pause.
Okay, so in theory, you assume every time's volume at the middle part of the band, right? In your theory, page 30.
Oh, yes.
So you assume that every time volume is in the middle of the next band, right?
Oh, yeah.
Okay. 3 minutes. Nice. Let's move on the discussion.
Okay, so I'm going to review the reporter says. So if you as the problem statement, the reporter wants to focusing on the properties of the muscle and about some volume properties. And and in their observation, they found that the body has a lot of like elastic, fatigue, and some volume properties, but they mentioned a lot of volume properties, but not the property they want to do. So I think they did not indicted about the property they want to do and focusing too much on the properties of the value. And as for the experiment, it doesn't define the pressure statement well because as you can see, the pressure in the reporter's slides it actually has a pretty big difference. So it should be defined into 3 kinds of states, and I think they didn't do it well because they have no definition. And for theory, they use a lot of not reasonable assumption, and they didn't connect the theory to the experimental well. And I want to invite reporter to the stage. So first, let me ask, what do you think is the most important parameters to affect the force?
Oh, so as you can see in the system, the force is applied by the balloon pushing outwards. It's pushing out.
I mean, why does the parameter affect the applied force?
So first of all, I would say that is the pressure difference.
Pressure. Okay,
Yeah.
so you mean pressure opposing the force, right?
Yeah, and so I want to clarify a little bit is that you mentioned about the pressure, and so for this report, throughout the report, the pressure we mean is the pressure measured by the BFP 280, which is the inside chamber and outside chamber's pressure.
Okay, so if you think, okay, so if you think the pressure is relevant parameter to the applied force, so and I can see in your graph the pressure is kind of linear, right?
You mean push part?
Like the M and the P.
Oh yeah.
Sure. Okay, so it's a linear. Okay, so why do you think it is?
Oh, you mean this part?
Yeah, why do you think it is?
Oh, this is the initial part, and this is the afterwards part.
Of course.
And so when the balloon is expanding, it tends to be kind of stabilized, and afterwards it's like this is the balloon.
Yeah.
And when we first inject the air inside, the air will push on the what do we say, the walls of the balloon. And when after time, when more air is injected, the force applied will tends to be kind of like stabilized by the pressure outbound, inbound, and also
my question is,
stress of
let me
the
just explain why the pressure will affect the applied force. So my question is, why is it linear? Why is it linear? Can you prove it?
Oh, so may I use this one? So as you can see over here, this is the Mooney-Rivlin model, and when combined with Laplace law, we can obtain this graph. So it's a mathematical model calculation. So we model it using that.
No, that's not my question. My question is, why isn't it linear? And you didn't show it. Because in formula, it no any parameter that is being in the applied force. Like, long as not applied force, the R is not applied force, and C1 and C2 is not applied force, so it's not explained well. I think it is a problem. And what I want to ask is, if the pressure is...
Wait a second. So, I forgot to tell you, but this one is actually this one.
Okay, so...
this one divided by this one.
No, actually, no, my question is, what is the parameter that the applied force, right?
Oh, yeah.
Then you say it is pressure. And in your experiment, you do apply like this, right?
Yeah.
Yes, so now I'm asking about this. So you didn't explain well. And next, I want to ask if the pressure is a band parameter affect the force. So if my net back is pretty hard, so you can just press it out. So if you apply the air into it, pressure will go out. So do you think the time will correct? Do you think if my net back is not expand, do you think although the inside pressure is going out, going up, do you think the applied force is going up too?
You mean like the direction or the value?
Value.
Oh, so when the pressure is growing, it indicates that first of all, actually the pressure is not only determined by the force, but also relatively the what we say the stress of the balloon and the net. So as you can see, what you just mentioned earlier is that the pressure increases and the force increases, but it's not actually that sort of such a direct relationship as the amount of weight. It depends on the amount of weight.
So you think the pressure is not only parameter dependent force, right?
Yeah. So
what are the parameters you think?
so also as you mentioned in the slide, it is also affected and determined by the applied external force. So it's like you're hanging weights underneath, and you're now pulling it upwards. And so when the pressure when the pressure increases, it also depends on the external force that you're trying to carry, the external weights that you're trying to carry. So the force will be dependent on that.
So okay, so as I thought you want to mention is that if you insert air into a volume, it will turn in one first pressure will go up, and then because the air pressure will go up, so because the net band is not pretty hard, so the volume and shape of the volume will be changed, right?
Yeah.
And then the change of the volume and this formation of the net band will turn in a applied force change.
And also it will cause the delta y to change, which is one of the y-axis. And when the delta y changes, it indicates that you're pulling things up. And so the pressure is determined by, first of all, the air injected, but also the pressure is determined by the external force that we are trying to apply.
So do you agree with this force chart? Then the pressure go up and then it turns into the formation for net band and the volume, and then it turns into force.
But also I think we need to include this one, which is the weight.
Okay, so you think the weight and the pressure will affect the formation?
Yeah.
So, but the weight.
And also the stress.
Okay, also the stress. Okay.
And the internal properties of the balloon itself.
But the weight is actually a force you apply.
Yeah, but actually, as we can see over there during our modeling and our experiments, this one and these are actually linked. They're linked. So what is that? Oh, that's just imagine you're a balloon, and you're applying a force over here,
Yeah.
and you're pulling it. Let's say a wall.
Okay.
And when you inject air inside and you limit the volume of it, and the pressure will definitely increase, right?
Yeah, sure.
And so these two are actually linked. As this one, you can think of it kind of like a wall, though it can be moved.
Okay, so you think this the W you mentioned here is like the trend of the net band. You restrict the volume of the volume, right?
Pardon?
So the W you mentioned here is like a trend of the net band to restrict the motion of the volume.
Kind of like that, but not exactly.
Okay, so,
Yeah.
okay. And then I want to move to the energy distribution. Because, okay, so if you apply it to inject the air into the volume, it will actually like the energy like this. Do you agree with this? The energy should be changed like this. Pressure, this is pressure, this is volume.
Oh.
Okay, so where do you think the energy goes? Because you apply the energy into the system, and where does it go?
Oh, you mean like when I apply energy into the balloon, where will the energy go?
Yeah.
So first of all, it will pull. It will definitely pull the things up. So it will give the delta U, the delta U of the object.
Okay, so
And also it will have what we explicitly mentioned, the elasticity.
yeah, elasticity.
And so elasticity.
But you say elasticity can be.
I mean the balloon.
Okay, so
The balloon, not the mass.
Okay, sure, okay.
Yeah.
But I think balloon elasticity can be considered in this part because the pressure is actually related to the elasticity of the balloon. So I think what you mentioned is this pressure and this kind of will be eventually going to like the applied force and the delta F. Do you agree with this? This is the applied force and this is the then change in the net. Do you agree? Because this is, yes.
But still, I would like to mention something is that there's also energy loss.
But they mentioned also energy loss. But do you think energy loss can be negative?
Not always.
Not always only. So
Yeah, so in our,
Okay,
where we mentioned about fatigue and other properties, so yeah, so it cannot directly be neglected as the material properties of a balloon will change over time.
Okay, so now what I want to go into talking about, I want to discussing about the delta U2, because in delta in pressure and force, time force dimension, it has a linear relation, but you can explain this well in the quantified model. You can explain it in the quantified model, and you can explain it in the theory. So I want to do is, if I'm talking about ideal model, so I can then the energy loss. So my pressure, volume, and the force, the relation can be looked at this. So if I use a
Wait a second. So the problem statement explicitly mentioned that we're talking about force, and why are you talking about energy here? Because I think we should focus more
let
regarding the force.
me complete my things. So and the energy distribution actually look like this in my model. We can actually do the relation between pressure and the applied force as this. So here this parameter is the applied force and this parameter is the pressure. So it means that I use my energy distribution to have a quantified explanation between a linear relation in your data.
But as you can see over here,
So yes, of course. I think before linear part actually is because you need to the pressure need to versus the elastic property of the body to split it out. So
yeah, that's why we mentioned about the stiffness.
yeah, of course, yes. I think yes. So I think you should split it. You should actually define the collision of the system into two parts. The first part is to versus the elastic properties of the volume, and next part is which is linear part, which I mentioned before. We can use this formula to quantify your data and explain that into your linear part. Do you agree with me?
Let me think about it. So you're suggesting that I just directly split the part? Is my understanding correct?
What are you talking about?
So as you mentioned earlier, you're saying that we should mention about stiffness over here.
Yeah.
But we mentioned earlier.
Yes. No. Everything I'm talking here is not about the stiffness. I'm only talking about linear part, and I have to define two states of a pressure into two states. And you mentioned everything. You mentioned everything in this part. Yes, you mentioned part one pretty clearly, but now I'm trying to do is I want to clarify and help you explain this part, linear part.
I want to clarify something. Is that
Yeah, sure.
External force is not the energy.
Okay, sure. No, because as a part statement, the net band will expand and shorten. So it will shorten. And the shorten will turn into the change of the length of the net band. So if you have applied force and you have a change of the length, it should actually be a work, right? So it is energy.
But this problem statement already tells us that we should focus on the force instead of talking about the energy, right?
So no, I'm not talking about energy. I'm just using this energy relation to derive this formula. And this formula can help you to know the relation between a force and the pressure.
I kind of see what you're talking about, and so yeah.
And sure, I think that is a pretty perfect explanation to linear, and I think that is we are finding about. And I think also in this part, I just mentioned that this part should be like the geometry, so it should actually be a constant or a function about the data in your model. Because you mentioned the data is right here, right? So I think that the geometry will affect these parameters.
OK，抬手。
Thank you. So for discussion, we mentioned about we separate the pressure and the force into two steps. The first step is versus the properties of the volumes, and the next step is talking about linear part. So we have them to use energy distribution to explain the linear part in a quantified way, and also we're talking about some deformation and the energy of the elastic to help them to change this way. And this is our basic flow chart. So I think we should first plot the volume and then so the pressure is actually first plot the volume and then before it touches the net band, the change of volume will a change of volume will affect the force, and which pressure is also affect volume. So we identify the relation between the pressure and the force. Okay, that's it. Thank you.
台长，那个 review time for.
First, I would like to ask both the reporter and the opponent. So, what both of you think is the most important factors that affect this phenomenon?
So I would like to express that is the deformation, and the deformation is caused by the pressure and the weight. And the weight is kind of like a constrained body towards the overall, which is why it's burdening towards the muscle stability.
Okay. So, what do you think?
I think it's the pressure and the deformation.
Also, in my opinion, I think it's also the pressure. And why did you choose to change the additional force rather than the volume of air passing through the balloon in your experiment?
So we've also mentioned the volume of air injected. So it's what was included in the pressure part.
It's like because you choose to change the additional force and you emphasize the additional force again and again. So why did you choose these factors rather than the volume of the air passing through the balloon?
Pardon?
It's like, why did you think that the additional force is such important?
Oh, because just as I mentioned earlier, it's the constrained body, which is the result of the pressure increasing. And so as you can see on the blackboard, the constrained body is one of the main source of constraining it, which is, in other words, burdening it from directly moving. So the operation will be kind of limited by the constrained body. And so we consider it as as one of the major considerations during my explanation, because that is the constrained body, which is you're tending to pull on, and so this pulling force is kind of like determinist towards this one. And so during the report, we also mentioned about stress and others, and those are the ones that we would like to majorly focus on.
Okay, so for the opponent, is there any force or anything you think that the reporter neglect that important?
I think that answer to measure the deformation of that back, because I think it's pretty important to know the deformation of that back, because it is directly affect the force.
Okay, thank you. That's all.
猜一下。
Pardon your remarks should be unplugged. Thank you very much.
So, I'm the reviewer of Team Max Coven Banana, and our topic is air muscle. So, first is the problem statement. And then the key points of the problem statement is the muscle properties and function of muscle under stress. Here's an overview of the report. The main theory are the first extension that divides the most, but it becomes stable later, and the error increases as building thinner. The main experiment is to find the effect of fatigue uses simple experiment, and balloon radius increases because of fatigue greater. The conclusion are fatigue is neglectable, ENF is linear, and balloon's reaction larger as the external force is larger. So does theory and experiment agree? The answer is yes. Then there are some remarks to the reporter of advantages, clear pictures and animation, and clear analyzation, and error rate. But the judgment for the report is too fast. Next is the remarks to the opponent. The advantages is competence, and there's some suggestions which is interrupting the reporter too frequently. Like you should listen to what the reporter said. The discussion is the most important parameters. So the reporter answered the pressure inside and outside chamber. So what is PF liner? The reporter explained by the data, and the opponent said it does not explain clear making formula. So I agree with the opponent, but it is not the only factor that affects. The volume difference because pressure. The reporter said that the force also affects, and the opponent said didn't consider. Is there energy loss or measure? The reporter said yes, but not always, but we have done. The opponent said it should be considered. I think it should be considered by dividing into different parts. Agree with the deformation of pressure is the force. The reporter said no. The opponent said yes, it should. And I think yes, bit wet and the stress will occur. Next is the energy neglected. The opponent said that the energy formula can be described with the linear part, and I think that not at all. So there's no missed points. So I asked both of the reporter and the opponent, what do you think is the most important factors that affect? So the opponent says it's the pressure, and the reporter said like lots of factors such as the force or the pressure or what he just mentioned on blackboard. So in conclusion, I think like the discussion between the opponent and the reporter on blackboard is a little bit emotional and it's quite fast. So sometimes I can understand right very well. So that's all.
Okay, the reporter takes the floor for the concluding remark.
Okay, so I'm the reporter, and so this will be my concluding remarks. So, first of all, we clarified qualified pressure using BMP-280, and we considered about the radius differences after several experiments. And energy is not an important discussion, since we only need to consider force according to the problem statement. And the opponent had drawn the wrong graph, trying to explain where these are wrong. And the linear part of the PF graph should be explained as balloon pulls the spring. And this is the remarks on the opponent's interpretation. and the opponent's mentioning of energy and force relation with expansion rates and the formation of the balloon. And our discussion, we talked about the relationship between the pressure and the force, and the opponent misinterprets external force. And why the F lambda performs linear, but our balloon model already proves the linear part. And we assume quasi-static since the balloon expands slowly. And we work hard to quantify as the phenomenon has energy loss and force. And so the force of external is no relevant to no equivalent towards the energy. And so for the remarks on the reviewer, I would like to say that she mentioned pretty much clearly on what I just tried to explain. Though I would still like to tell her opponent that this graph is actually wrong. Thank you.
Okay. So we move on the question from the juries. Any question? Professor Xu.
One question for the reporter. So what property of muscle have you investigated? You were supposing that which part of your data? What property of muscle have you investigated?
So the properties of muscle, so we investigated first of all the motion under weight pressure, underneath, and we also talked about the stress.
So what's the response of muscle to the weight?
You mean a response of the muscle to the external weight supply?
Yes.
So as you can see in our slide, can I use this slide? So as you can see over here, this is the weight applied versus the time. And the rate of increase of muscle generated force decreases over time, as you can see in this graph.
This is muscle response.
Yeah.
And how is this related to your data?
You mean related to our which data?
You are describing this property. So what data are you describing?
You mean that what do you mean? Sorry.
You are trying to study muscle property through air net.
Yeah.
So that property of muscle, what kind of experiment do you do to describe that behavior?
Oh, so what we mentioned earlier, we mentioned about the balloon, and we first focus on the balloon itself, which is the main source of the pushing force outwards, and we then talk about stress. The stress part is applied using the setup, where we apply the net and the balloon inside. So before this slide, we're mainly talking about the balloon, which is the main source of all this action, and then next we consider net as sort of a direction changing one, where, as you can see over here, the net is kind of like changing, manipulating the direction of force.
Your data matching the property.
Pardon?
Your data matching the muscle property.
Oh, because of fatigue and other reasons. So, where's that? Yeah. So we talked about the fatigue part, and so as you can see over here, this is the part that we were mentioning about the fatigue, and so the fatigue one, and the slide we mentioned.
The muscle is same fatigue property.
Huh?
So you try to explain your data with fatigue phenomena, not the force response.
So it's like we're trying to measure the fatigue because we want to say that the fatigue can be neglected so that we can do multiple experiments.
Yeah, so
because different balloons have different material properties.
Data supporting.
Sorry,
What's your data supporting the muscle property?
Fatigue decreases over time.
So this is how you describe muscle property?
It's like we described about the fatigue decreasing over time, and we talked about the stress. So so we use the fatigue of the balloon to allow us to do multiple experiments. fatigue decaying, and we talked about the stress and the and the reactions towards the pressure of the exterior and the interior.
Okay, thank you.
I want to point out a critical question from the opponent. You critique the reporter about the linear relationship
Yes.
between the force and the pressure.
Yeah.
Pressure. And I think that's, can you just very simple explain why dl over dv is a constant?
No, actually, that is the geometry, and it is B is volume and L is the length, so it's all about geometry. So after I do the DL divided to dp is actually a function of the data over like that. So it's actually not related to the pressure. So yes, it should be a constant.
Should be constant.
Yes.
And both of you agree with the opponent?
So first I would like to clarify a little bit is that this graph is actually wrong. So we have explicitly mentioned that this graph is actually wrong, and this should be the pressure and this should be the force, and it's not like this bumpy part that's like a little bit upward and going this way. So we can actually say that this one is pretty much wrong, as this bumpy part only exists in the one with the lambda one. The P lambda graph, it's only in the P lambda graph. And so, as you can see over here, this one stays with our formally mentioned theories, and that, as you can see, when there's a balloon, when we inject air inside, the pressure will increase, right? And so, when the pressure increases, we can say that the force is actually increasing, as force and pressure have a what we say a relationship or correlation.
So I think I will agree with the opponent. I think it will be constant.
Any other issue?
I have only one question about the problem. The problem say a balloon inside a net, then the net will expand and shorten, right?
Yeah.
And investigate the problem of such muscle. So my problem is, what is the muscle if you can only choose the net or the balloon? One of them.
Net.
What's the meaning of muscle?
I think it's net.
Net.
Yes, net.
Net.
And what's the
So the muscle generating force is mainly sticking to.
muscle or net?
What do you mean?
Balloon or net?
Oh,
What's
so
the
the
meaning of
balloon.
muscle?
The balloon is what is the main source, and as I just mentioned earlier, the net is only used to change the direction of the force applying.
You can only choose one. The muscle means balloon or net.
The balloon.
Any other question? Okay, let's restore. Okay, the score for the reporter. 6, 7, 6, 7, 7. And the score for the opponent. 6, 8, 7, 8, 6. And for the reviewer, 6, 6, 5, 7, 6. Okay, and so this session will be closed, and we will take 15 minutes for rest.